Hi, this is Chrisferb, and I'm going to review coefficient of variation calculation. So a couple things real quick. The reason why we use coefficient variation is we're trying to determine the relative dispersion or variance within a calculation. And the times that we use that, within a distribution. The times that we use that is when we're comparing two different distributions and the data is in different forms, so it's hard to match it up. If you could imagine hours or gallons or something, two different, totally different measurements type of deal. And the other thing is we're just looking at the spread or the variation within the distribution. We're not matching it to one point in time, which we do with the z-score. If you remember, with a z-score, we end up with an x value, and then we kind of compare that, or we subtract the mean from it, and then divide it by standard deviation. In this one, we're just doing the relative dispersion. The other thing is, a couple other things. The answer for this one is in a percentage form. Let's see, another thing is the data that you're given for this one compared to the z-score calculation. We only have the standard deviation and the mean. We don't have an x value like a data point. And so it's mainly just to see how much spread there is within a very distribution. Okay. Oh, and like I said, this one, the answer is in a percentage, and the z-score calculation is an indexed type of standard deviation measurement away from the mean. So when the z-score says 2.57 for your answer, that means it's 2.57 standard deviations away from the mean, where this one is a percentage and it's talking about the spread. Okay, and I'm talking about the coefficient of variation versus the z-score calculation because people get them confused. Okay, so just remember those points that I mentioned. Okay, I have no idea if this data is even close. I made it up. Okay, it says a study performed to measure the length of arms versus legs resulted in the following data. Okay, arms. This is the mean, that's the sample standard deviation. Now you could use this whether we're using sample data or population data. It doesn't really matter, okay? You just, you would just use the population standard deviation, and you use mu instead of our sample mean, okay? So it says compare the relative dispersion of the two distributions. So we want to see which one has more spread, more relative dispersion. Okay, let's see. Okay, so the formula is like this. The formula is CV, and like I said, whether it's population or sample data, doesn't really matter for calculation. Okay, let's see. So it is the X bar or this. So we put the standard deviation on top and the sample mean on the bottom. Okay, and then we multiply it by 100. That makes it a percent for us. Okay. Okay, let's take a look at the arms. Make sure I'm all lined up. So for the arms, it is going to be this. And that goes below. And then this one is above. Then we multiply it by 100. Okay? So it ends up being like, let's see, 0.08333 multiply. Once we have it multiplied by 100, you end up with this. About 8.3333 on forever percent. Okay, so about 8.33%. That's arms, and then legs. CV. Let's see, standard deviation. Standard deviation up top. I always have to look at these to make sure because it's not a common calculation for me. Let's see. Yes, standard deviation up top, so that's 4, and then 90 below. Okay. Yeah, it's not a super common thing, computing the coefficient of variation, but if you need to compare things, it's useful for that, compare distributions. Okay, so the answer for this one is 4.444%, so about 4.44%. Okay, so the one that has more dispersion is the arms. In this case, who knows? I just made up the data. Okay? Well, thank you for watching.